Okay, so last time we talked about, the last few times we've been talking about internal loads, and we kind of took a detour. We'd been talking about how to calculate stresses and strains due to uniaxial tension and compression, and then we took sort of this detour to talk about how to calculate internal loads. And so where we're going with that is now we're going to come back to talking about how to calculate stresses due to the shear force and the bending moment that came up in the internal loads diagrams. So all of those problems that we've been doing with beams, calculating the internal loads, now we're going to be able to calculate what the stresses are at any given point. So I'm going to start by talking about stresses due to bending moments. Those calculations are a little simpler, so that's why people usually start with those. I want to first, I want to point something out here. When you do those internal load calculations, you calculate a shear force, a bending moment, and a tension at a given cross-section of a beam. Those are all vector, well, two of them are vector forces, and the other one is a couple. And how do those combine? Well, they combine as vectors, so you can just add them together and get a single vector, right? What happens now with the stresses? So say that you have a beam that has, we already know what to do with tension and compression, right? So say that you have a beam that at a point has an internal tension, and at that point it also has an internal bending moment, okay? So say that we calculate the stress due to the tension compression, and then separately calculate the stress due to the bending moment. How do we combine those into a single state of stress? That's important, right? I mean, otherwise we'd only be able to deal with beams that had tension compression, or had bending moment, or had a shear force. Well, you add them the same way. Just as component vectors add, stress tensors due to individual loads add element by element. So, for example, if you had a stress tensor that you calculated due to tension that was equal to, 50 megapascals, and you had a stress due to bending that was equal to negative 40, 0, 0, everything else is zeros. And you had a stress tensor due to shear force that was equal to 0, positive 20. It has to be symmetric, so there'd be a 20 there, and everything else zeros. And say that all of these are happening at a single point, then at that point the stress tensor would be 50 minus 40, so positive 10 megapascals, 0 plus 0 plus 20. So that's nice. That happens easily. And this is a consequence of the fact that we're dealing with small deformations. So if you then go into trying to do calculations for a material and loading where you have big deformations, it gets a lot more complicated than this. Okay, so that's good news. So we can calculate the stress tensor due to tension compression, calculate the stress tensor due to bending, calculate the stress tensor due to shear, do all of those independently, and then just add them together and you get the final stress tensor. So we're going to calculate the stress due to bending moments. What are the beam requirements? For our bending calculations. Well, first, and let me set this up as so in each of these, I'm going to give an example of what we can calculate and what we can't do calculations for. So can do and can't do. Okay, so the first requirement is that the member be straight. So we can do beams like this, but with this approach, we can't do stresses on something that's undeformed shape is curved. Second, the beams have to be prismatic. So we can do that, but we can't do something where the cross-section changes as you go down the beam. And third, the cross-section of the beam has to be symmetric about a vertical axis. Now I'm assuming bending in the direction that all of our bending moment diagrams have been. So that's assuming that the bending moment is about a horizontal axis. Then there has to be symmetry about a vertical axis. So we could do a cross section like this, but we couldn't do a cross section like this. So these two are cross sections of the beam. There are ways to approach these things, but the calculations that I'm giving you right now don't work for any of these in this column.
Would you explain it a little bit with the third one?
Yeah. So this would be so this is symmetric about this vertical line. Okay, like it's a mirror image across. This one, there's no vertical line that you can draw. It's symmetric about this line, but that's horizontal, so it has to be vertical. Okay, so what kind of stresses can we expect from bending? So how are stresses developed in bending? So if your undeformed shape is this, and after deformation, this is exaggerated because this wouldn't be a small deformation. But after deformation, it looks something like that. Then I want you to pay attention to 3 lines, okay? So one right down the middle. In both cases. And then one near the top. And one near the bottom. And think, what happens to the length of these 3 lines as this deformation happens? And if we think, just like we've been doing for the internal loads problems, the x-axis goes along the long axis of the beam. You can probably imagine that the green line has to get shorter, the blue line has to get longer, and somewhere in between them, and we don't know exactly where yet, it stays the same length, okay? So for a positive bending moment, let's say material lines near the top get compressed. Material lines near the bottom get stretched. And in between, somewhere, there has to be a line that stays the same length after deformation. This line is related to what we're going to call the neutral axis. And that's going to be an important starting point in doing these calculations. Okay, so what kind of strains do we see? We know that in the x direction, that green line is getting shorter. In the x direction, the blue line is getting longer. So what element of strain do we have there? I mean, is it a shear strain? What is it? It's tension and compression. So even though this isn't uniaxial tension and compression, the only stress and strain that's going to happen due to bending is a normal stress and a normal strain. Bending only causes normal stress and normal strain. Okay, so I have to give two, before we can go into how to calculate the stress, I'm going to give two sort of mathematical definitions that this is going to be based on. The first one is the neutral axis. So find the centroid of the cross section. The neutral axis is the horizontal line through the cross section that intersects the centroid. Okay, so if you have a beam like this, and let's set up the coordinate system with the x-axis going down the long axis of the beam, the y-axis going up, and the z-axis coming out of the page. Then the neutral axis is where we're going to put that's where the z-axis is going to be oriented. So this is the centroid. That's x, y, and z. Place the z-axis along the neutral axis. Okay. So what if we had what if the cross section was a right triangle? Where would we put the neutral axis? Let's say well, the centroid is going to be I guess if we call this L, let's say that's L2, then the centroid is going to have to be L over 3 that way, L over 3 that way, then the y-axis is going to point up, and the z-axis is going to point that way. And the neutral axis is this. Because, so I'm imagining this like looking, I'm looking down the x-axis. So this is the neutral axis. And you can find that point however you can find a centroid. Like in some complicated problems, you'd have to do it as an integration. But when we do it, it's always just going to be based on formulas. And notice that you could also, just like you do with, we do in other centroid problems, you could build up these shapes. You could have two rectangular shapes that make like a T shape. And you could use the centroid sum formula to calculate where the centroid is of that T shape, which is useful because some beams have that kind of shape. Okay, the second mathematical preliminary we need is called the areal moment of inertia. And this moment of inertia is calculated about an axis. People tend to just call it the moment of inertia, so I'm going to put areal in parentheses and about an axis in parentheses, but in order to understand what you're doing, you have to sort of keep these in mind. And this is a calculation of, it's a measurement of how resistant to bending the cross-sectional shape is. Okay, there's something important to notice about this. This is not the same thing as the mass moment of inertia. From dynamics. So this makes it seem even more ridiculous. The mass moment of inertia, people also call simply the moment of inertia. So people also simply call that the moment of inertia. And both are represented by a capital I. Okay, that seems like it's just asking for trouble, like in understanding. And I've talked to a lot of people who've finished engineering school, finished master's degrees or whatever, and never noticed that those two things are different things. But one is a resistance to bending, and one is a resistance to rotation. Okay. So the formula for the aerial moment of inertia I is the integral over the cross-sectional area of y squared dA where y is the distance from the increment of area to the chosen axis. And for us, that's usually going to be the neutral axis. And that chosen axis is when I said that the aerial moment of inertia about an axis, it's the axis that we're taking the moment of inertia about. Okay, that's the axis I'm talking about. Okay, so we're not going to do this as an integral calculation. We're going to follow formulas the same way we did for centroids. But let's do one calculation of the moment of inertia for a rectangular cross-section. So here's an integral example. So I'm going to find the moment of inertia formula for a rectangular cross-section. Okay, so say that the cross-section has width W and let me make one more clarification here. We're going to find the formula for a rectangular cross-section about its neutral axis. So about a horizontal line that goes through the centroid of this rectangle. The height is h. The neutral axis is this. It has to be a horizontal line and it has to go through the centroid of the shape. And then I'm going to use this coordinate system with y pointing up and z pointing this way. Again, this would be like looking straight into the arrow side of the x-axis. And okay, so if we're going to use that area for the integral formula, how are we going to define our increments of area? Again, like with this, that's sort of the key is finding a good way to define the increments of area. Do you want to do like clover-shaped, like infinitesimal clover-shaped areas? I don't know. Let's not. That would be challenging.
What's the formula?
The formula for a clover? Well, I guess we'd probably have to do an integral to figure that out too. But
Make it like a quintuple integral.
instead, how about this instead?
Let's do it in Polish.
So the clover thing popped into my mind first, but how about this? This seems better actually. How about just thin strips like this? Okay. So the thickness is dy. This distance is y. And so then the moment of inertia is y squared times an increment of area, which is y times, no, it's not y. It's an increment of area is w times dy, right? It's the width of that skinny rectangle times its height. Okay. That's all I wanted. One thumbs up from somebody. So you got this. And then what are the boundaries of the integration? We're doing it with respect to y. Yeah, negative h over 2 to positive h over 2. And so you get w y to the third over 3 evaluated from negative h over 2 to h over 2. Substitute in the h's, and you get w h to the third over 12. Okay, so this is the formula we're going to use the most often. Question?
Yeah, I have a question about sort of the definition of our aerial axis.
The neutral axis?
The neutral axis,
Yeah.
right? That's defined by the direction we're going to be bending, right? So
That's
we
right.
bend
So we're assuming that we're always bending about a horizontal axis,
Sure.
like we have in problems.
Sure, but we could bend by a horizontal axis that's, we're not bending this way,
Oh,
but this way, right?
yes, but if you do that, horizontal, so you're talking about bending,
See if we had a square,
yeah,
right?
Right.
And then we're bending it like this,
Yeah.
basically, like either this or like
Right.
this, right? If we had a square and we turned it this way, we could still bend it like
Mhm.
this. It'd just
Yeah.
be, the points would be on top.
Right. Well, mostly we're going to be doing long beams, and the bending is only going to be about, so there are really only going to be two options that we're going to worry about. Bending about the y-axis, as I have it drawn here, and bending about the z-axis. The reason for that is that issue with St. Venant's principle. If you have something that's like a square, and you only trust your results within the width of the loaded side, you know what I mean?
Yeah.
Like okay, so if you have a square, and before you trust your results, you have to get, and say you have a square and the top and bottom are loaded, okay? And now to trust your results, you have to get the length of that loaded side away from the loaded side to trust anything. That means that you don't trust anything in the whole shape. Okay? And so that's why our calculations are going to involve things that are a lot longer than they are than the loaded side
Sure.
is, you know?
I was kind of thinking about something that's not, the total beam is the shape of the square, but the cross section is the shape of the square.
Mhm.
Like it sort of is here.
Yeah.
But instead of bending, like, say we have like a bending axis.
Right.
So here's our square.
Yep.
We're bending like this, right?
Right.
Where our flat side is to the top.
Right.
Or to the bottom where we're bending,
Yeah.
right? But we could also have it like the flat side is sort of skewed to the side where we could still be
Yeah.
a cross-section of a square.
Yeah, right. We won't worry about that, and I guess that's just because things don't tend to fail that way. That's just not a concern usually.
Sure.
But yeah, mathematically, you're totally right about that. Okay, so this is the formula for a rectangular cross section. So notice that the height of the rectangle is much more important to the ability to resist bending than the width is. And how does that show up in that formula? Why am I saying that?
Makes sense though, right?
It makes total sense, yeah.
Lead to the bend.
Yes, that's exactly right.
This would be much harder to bend.
Exactly, yep. So what in this formula says that?
The cubic power. of
Yeah,
the
that's right. The height is cubed, the width is linear. And so, and you can imagine imagine a meter stick. It's very easy to bend the thin way, but if you turn it up and try to bend it when, where you can actually see the numbers, it's hard to bend, okay? This fact is going to end up being the main engineering consideration in why I-beams are shaped the way they are. And Rich, that's that's related to the thing about that bridge that you were building, like if you're trying to resist bending along this axis, you want to use most of your material to make it tall, And I think we all sort of intuitively understand that, but mathematically, this is why it is. Okay. Okay, one more formula. So you can think of this as the moment of inertia for rectangular cross section. If you have a circular cross section, the formula is pi r to the 4th over 4. So what are the SI units for areal moment of inertia? Fourth, yep. Meters to the 4th. Okay, two useful things about moment of inertia. So two mathematical facts about I that will be useful to us. The first one is that I follows the parallel axis theorem. The parallel axis theorem says, so if this is your cross section, and this is the neutral axis, and say that you want to calculate the moment of inertia about this axis, that's a distance d from the neutral axis, then the moment of inertia about A is equal to the moment of inertia about the neutral axis plus AD squared. Okay, so that in itself, you might not recognize yet why this is important to us, because why would we ever want to calculate the moment of inertia about something other than the neutral axis? Okay. But the reason that we do is because of the second fact, and that is that we can add moments of inertia to build up shapes out of simple shapes. So an example where we would do this is with an I-beam or a T-shaped beam. So let me do an example for an I-beam. By the way, before I go on, what about the mass moment of inertia? I don't think in dynamics you guys have gotten to talking about rigid bodies yet, but you probably talked about this in physics, right? In physics 1. So what about the mass moment of inertia? Is there a parallel axis theorem for the mass moment of inertia? Yes. So that's another confusing thing about these two. And can you figure out the mass moment of inertia by adding up individual mass moments of inertia? Yeah. So there's so many similarities between these things. And that's why I'm sort of beating this to death, I guess. But these are totally different things. They measure different properties of a material. Just about everything else about them looks identical, though, so be careful. Yeah.
So doing your moments about A, is that just for like saying a rigid body with a centroid on the neutral axis or something?
Yeah, and so the way that's going to work is, I guess I'll do the example problem next time. But like imagine an I-beam. So we're going to do this as 3 rectangles, right? Except the formula gives us, so we're going to break it up into this rectangle, the middle rectangle, and the bottom rectangle. The problem is the formula gives us the moment of inertia of the top rectangle about this axis, the middle rectangle about this axis, and the bottom rectangle about this axis. But we need the moment of inertia of the top one about the moment of inertia about the neutral axis of the whole shape, the middle one about the moment of inertia, the neutral axis of the whole shape, and the bottom one about the neutral axis of the whole shape. And so we'll use the formula to get this about its neutral axis, then the parallel axis theorem to figure out what the moment of inertia of the top rectangle would be about the true neutral axis, and then finally add up all those pieces. Okay. Any questions about that? So I guess I'll start with that calculation next time. Oh, and no school on Monday, President's Day. I know. There have been a lot of Mondays off this semester.